Hi everyone, my name is Wang. I'm from Music and Audio Research Lab at NYU. I'm going to present Few Shots Sound Event Detection, which was an intern project with Adobe Research. If we think about the daily workflow of podcasters, audio engineers, soundtrack editors, and animators, one of the common things they do a lot is finding specific repeating sound events in a long recording. For instance, a podcaster have to find and edit out filler words like ums and ahs to improve the flow of speech. Audio engineers often need to locate similar musical events such as a drum hit to fix issues and add effects. Soundtrack editors need to find similar words spoken by the same actor to perform dialogue replacement. Animators need to locate particular sound events such as footsteps to synchronize motion graphics. Nowadays, to find repeating sound events in a recording, you have to listen through the whole track and manually label every single event one by one, until you look like this. So the goal of this work is trying to make this process easier and more powerful by designing a search by example sound event detection paradigm, where the user only select one or a few examples of the target sound. The machine then automatically locates everywhere else where similar sounds occur in an audio track. There are three main characteristics of our proposed system. First, no prior knowledge of the target sound event. We want to be able to search for any sound in the recording. Second, minimal human effort. Ideally, we only label up to 5 examples of the target event. Lastly, the system needs to provide real-time, on-the-fly detection. Once we select the target sound, the system should be able to quickly adapt to it and display the location of the detection. It is challenging for standard supervised machine learning techniques to meet these characteristics, since they typically require a large amount of data and time for training. Standard multi-class or multi-label detector wouldn't work well, because we don't even know what class to look for before users make their selection. Even if we do transfer learning, 5 labeled examples are not enough for fine-tuning either. To overcome these challenges, we propose to leverage few-shot learning methods, which has many appealing properties for our application. It is a learning paradigm that aims to learn a model which can quickly adapt to unseen classes by seeing very few examples. In standard supervised machine learning setup, we use a large training set to train classification model. Here is an example of training a handwritten digit classifier. Then at inference, the model classifies new examples of seen classes. For few-shot learning, we also train the model with a large training set, but at inference, the model sees a completely new class. If we provide an additional support set, which consists of few examples of novel classes, 1, 2, or 3 examples per class, few-shot model is then able to point out to the correct class within the support set. The ability of a model to perform few-shot learning is typically measured by its performance on C-way K-shot classification task, where C represents the number of novel classes and K is the number of labeled examples per class. Here is an example of 5-way 2-shot classification, where a color represents a class. The task is to label a query with one of the 5 class labels, given 2 labeled examples per class. While there are many different approaches to train such model, in this work we focus on metric-based approach. It has a simple framework and allows feed-forward inference, which are ideal for our application. Given a support set, the goal of a metric-based method is to embed the support and query examples into a discriminative embedding space using a neural network F, and correctly classify the query by measuring the similarity between the query and support embeddings with G, which can be a fixed or learned metric function. To train such model, people use episodic training strategy, which matches training and testing objectives. In each training iteration, the support set is sampled from a large training set. The model is then trained directly on a C-way K-shot classification problem by minimizing the classification loss of queries. In each training episode, we resample the support set so that it contains different classes. After training on many episodes, the model learns a class-agnostic comparing ability. Our next step is to apply the trained few-shot model to sound event detection to look for sounds in the recording that sound similar to the target. First, we can take the human annotated example as the support example for positive class. Then divide the audio track into a series of query frames and classify if a query frame belongs to the target class or not. Since few-shot model does close-set labeling, we view this detection problem as binary classification, where the negative class represents all non-target sounds. But how do we construct the support set for negative class? From the human effort point of view, we don't want to ask for additional labels. So we come up with a strategy to get negative examples by randomly selecting frames from the track, with the assumption that the target sound event is reasonably sparse. This could, of course, introduce some label noise, but later in our results we'll show that overall it works pretty well, and it doesn't require additional human effort. Now we have our complete setup for few-shot sound event detection. This approach is applicable to a variety of audio domains such as speech, music, and environmental sounds. We evaluate the proposed approach on speech in this work due to the size of available data. We used the Spoken Wikipedia Corpora for experiments. It contains audio recordings from volunteer readers reading Wikipedia articles. We use a word-aligned subset containing about 700,000 aligned words, 183 speakers, and about 9,000 classes, where a class is defined as a word spoken by a specific speaker. We filter words to only keep those have been spoken frequently. On average, the vocab size of each speaker is about 50. The speakers and their corresponding word classes are partitioned into train, validation, and test splits. To train the few-shot model on SWC, we construct each training episode by first randomly sample one speaker from the set of training speakers, then sample a subset of words from the chosen speaker as the support set. We experiment with several variants at training. First, we adapt different existing metric-based few-shot learning methods, including Siamese networks, matching networks, prototypical networks, and relation networks. For all of these methods, we use a standard CNN for the embedding module F. It consists of 4 conf blocks. The input to the embedding model is a log-mel spectrogram computed from half-second audio. The main difference between these methods is the similarity module G, or the distance metric used to measure the similarity between the support and query embeddings to predict query labels. Siamese networks serve as the baseline in this work. They do not incorporate episodic training with few-shot classification. Instead, they are trained using pair data from the same or different classes, with triplet loss and L1 distance as the metric. Matching networks compute the cosine distance between the query embedding and each support embedding for classification. Prototypical networks compute the square Euclidean distance between the query embedding and the class mean of each support embedding. Relation networks replace the fixed distance metrics with the learnable CNN. Then we also vary C and K to see the effect of support set configuration at training. Evaluation is based on the detection of unseen word classes in our test set recordings. We use 96 recordings from the test speakers in SWC. In each recording, we pick up to 10 target words. AUPRC average over all recordings is used as the performance metric. We also experiment with several variants at inference. First, varying the number of randomly selected frames as the negative examples. Second, varying the number of positive examples. Lastly, to further reduce user labeling effort, we propose a novel strategy for augmenting the positive examples. Take a user selection. We shift the selection window in both directions in time by 50 millisecond increments to generate additional positive examples and see if this can further improve the detection. Now I'm going to show the results from all experiments where we systematically vary each parameters while everything else are fixed and see how they affect model performance. First of all, prototypical networks achieve best performance among 4 different methods. It also has one of the simplest algorithm and fast inference. The following results will be based on prototypical networks. For support set configuration at training, we found that increasing C, the number of ways, give better results. A higher number of ways during training makes the classification task harder, forcing the model to learn a more discriminative embedding space. The results here are evaluated with 5 shots at inference, where p equals 5. We found that matching the number of shots between training and testing gives best performance. This has been shown as one of the characteristics of prototypical networks in previous study. At inference, first thing we need to solve is negative class modeling. We proposed to randomly sample n examples from the track without additional human labeling effort. We found that this actually works, and the best results is achieved when n equals all, which means we can just take all frames of the recording, the whole track, to model negative class. This is great in application since we can compute all negative embeddings in one go. For positive class modeling at inference, model performance increases when we have more positive examples, which matches the intuition. But we also see that the relative increase in performance diminishes as P gets larger. Having more than one positive example is definitely good, but when annotation cost is high, we can limit ourselves to 5 or a bit less examples without compromising too much in performance. For inference-time data augmentation, we experiment with including different number of shifted windows as additional positive examples. 0 shifts means no augmentation. 2 and 4 shifts means including 1 or 2 neighboring windows in both directions of the original positive examples. At first, we see little improvement with this augmentation. A possible reason is our use of a fixed half-second context window. For words shorter than half a second, the context window may include noise, while words longer than half a second are not fully captured. In both cases, the augmentation may not result in a better representation. If we limit the target keywords to those with duration close to half second, we start seeing a significant improvement. Including 2 shifts gives an 11.4 percentage point boost when we only have one positive example to begin with. The effect of augmentation becomes less significant for increasing number of shift and P, as the variation between additional examples generated by augmentation become less significant. So overall, our best model achieved more than 75% AUPRC on keyword detection. This model is trained and tested on English. Now we have a question. Can we test our model on other language? Since theoretically, our approach is completely language agnostic and does not rely on speech recognition at inference time. The answer is yes. Our model, trained on English recording only, shows compatible performance when testing on Dutch and German. Our model is able to recognize similar sound events in a way that is robust to cross-language differences. To recap, we saw the problem that finding similar sounding events in recordings is tedious. We propose to view this as an open-set sound event detection problem and tackle it using few-shot learning. We found that among different methods we've tried, prototypical networks work well and are fast in inference time. At training, we found that increasing C, the number of ways in an episode, improved model performance. At inference, we found that we can use the entire recording to model negative class. And inference time data augmentation is beneficial if we only have very little positive examples to begin with. We also show that our model trained on English only generalizes well to other languages. We are now looking into if it even generalizes to other audio domains. The main limitation of our current system is that it has only been trained and evaluated on monophonic audio signal. Now we are also looking at generalizing the idea to polyphonic audio. Lastly, I'm going to do a quick demo of how our system works in real-world scenario. Feel free to also check out a longer version on YouTube by searching Project SoundSeek, or just copy and paste this URL. Let's say I want to find all the us in a recording sounds like this.
Hi everyone, I'm very excited to be here today and show you a cool new technology we've been working on.
With our few-shot sound event detection system, we can select one example and hit Analyze to feed into the model. The model will then show this red detection curve immediately. Let's have a listen. That's it. Thanks for watching my presentation, and I hope you all stay safe and healthy.